Hi everybody, my name is Lalitha Sankar and I'm an associate professor at Arizona State. I'm going to talk about using federated learning to build a contact tracing application that can be used to track COVID-19. It builds upon some of the already known concepts in contact tracing, and it also uses on-device analytics to do it. This is joint work with my colleagues Annie True, Ming Zhao, and Visal Berisha. All of us are at ASU. So very briefly, contact tracing is the problem of identifying all the individuals that may have come in contact with a person who is being diagnosed with an infectious disease. Right now, we're in the midst of a pandemic related to the spread of COVID-19, a disease that's caused by the novel coronavirus, and there is much need for contact tracing. Traditionally and historically, contact tracing has been done manually, and even now in the United States, it's being deployed manually in many states. That involves people going door to door to do this work of alerting, isolating, and testing people, but it can also be enhanced to track a wider spread of people than those you personally know that you came in contact with if you were infected. And that's using smartphones. To explain how it works on a smartphone, let's look at a particular contact tracing application that's been developed and will soon be deployed by Apple and Google. So the way this works is that, say there are two parties, A and B, and they've both downloaded this contact tracing application on their phones. When they are in close proximity to each other, their phones share a key code, a token, based on their Bluetooth codes with one another. And this is then recorded by the app. If one of them, say A, gets infected, then A or a trusted healthcare provider updates their status on the app and then gives the app permission to share their Bluetooth key with the central server or the central database. Since every user like B has downloaded the app and agreed to use it, their app continually downloads the database of infected people from the server, and since B was in contact with A and A is now being infected, B is notified that somebody she's in contact with has been infected and she should take the right precautions. The identity of A will never be revealed because the server themselves does not know the identity. The key shared is an encrypted key of the Bluetooth device. Now, this is really a very cool idea, but there are a few limitations to this. One is it is actually vulnerable to attackers who can collect the key codes of others and rebroadcast them, leading to a large number of false positives. Also, since it does not use any kind of location-based identification, you cannot track, using contact tracing apps, this kind of contact tracing app, hotspot locations. Finally, the app also does not use all kinds of rich user-specific data on the device that could be correlated with either having the disease or having a higher risk of the disease. And those are the kinds of things we want to explore in this project, and we are doing so. So the first thing that we are working on right now, our project has two parts. One is on the contact tracing itself, and the other is on the on-device learning. So in terms of contact tracing, what we want to do is combine both Bluetooth and GPS to learn a more enhanced contact tracing graph. So the Bluetooth will be used for peer-to-peer and building the local graph, and the Bluetooth plus GPS will be used for communication with the server and especially to learn the infected hotspot histogram. In terms of the device, what we want to do is to use a combination of surveys and mobility patterns as well as some kinds of biomarkers to continually assess risk. So let's go into each one of these in detail, and here's a visualization of our work. Effectively, every user is going to use both Bluetooth and GPS, and this will be sent in an encrypted manner so that we can do oblivious aggregation. Users, on the other hand, have a model that's been learned in a federated manner that uses a bunch of locally captured data, which in turn determines a risk score for the user And this risk score can be used to actually come up with a more nuanced notion of a hotspot histogram. So let's look at the contact tracing aspects. So here again, A and B are two parties. When they meet, they're going to share in a peer-to-peer fashion their Bluetooth key codes, and their phone also locally records their location lengths. So when A becomes infected, now A is going to share its GPS location hashed with its Bluetooth key code, and because of the timing logs, the server can actually obliviously figure out when, where, and whom A met, right? So this alleviates the rebroadcasting attack or the replay attack. So this work is largely going to build on my colleague Neetru's expertise in this area, including her recent work on EPI1, which is based on a Bluetooth-based system. So there's a lot more work to be done in incorporating GPS. So the immediate question is, how does this help us actually compute hotspots? Here, what we are going to do as a first cut is to identify a set of locations for which we want to compute the frequency of infected users coming in. So for example, if this was deployed on the ASU campus, we could have a whole bunch of buildings on campus that a lot of students go to as our list of places, it's a vector, that a user can go to. So if a user who's been infected has been to any one of those places, then the binary vector associated with that user will toggle the 0 to a 1 at that location. And this is what a user, when they're infected, and for about 14 days after they're infected, will continually upload to the cloud. Right? So there is a genuinely fundamental problem in this case, because if you were doing this not just on a campus, but across cities, towns, even states, the length of this vector can blow up very quickly. And one way to solve that problem could be looking at heavy hitters and saying, we only collect this kind of information for certain places that we either identify as hotspots, say retail locations, malls, hospitals, childcare centers, and so on. And as we go along, you take the ones that go beyond a certain threshold. That was for the contact tracing part of the application. For the on-device side, what we want to do is to combine some kind of a baseline risk based on a survey. And this one, we will use an existing survey built by closedloop.ai. And then we want to use a predictive model for mobility-based risk and a predictive model for a particular biomarker, which is phonation-based. All of this is going to involve using federated learning, and that's what I'll talk about now. So let's look at each one of these features in detail. So the baseline feature is based on this recent work by folks at this company called closedloop.ai. And the way they did this, they took 1 year's worth of data of people who have upper respiratory disorders, and they use as proxy for having complications from COVID or increased risk to COVID-19. The proxy used is those who had complications, and the particular complication was getting hospitalized following an upper respiratory disorder. So they had all this data, and the label was basically hospitalization, and that would be a proxy for COVID risk, high COVID risk. So effectively what the model does is it does a one-time survey. So if you go on their website, you can take this survey of all kinds of diseases you may have had, or you have, or you're at risk at, including diabetes and heart diseases. What they've done is they've built a logistic model. So when you take it, basically it predicts a risk score using the logistic model's weights. So that's what we can incorporate firsthand, simply in a direct fashion. The other two features are what we want to build on more, and one of them is going to be GPS mobility patterns. So now every user has access locally on the device to its own mobility pattern. Certainly, based on infected users, you can estimate the infected hotspots. But perhaps what you can also do is, using users' mobility, say, for example, within ASU, we can also come up with a histogram of mobility-based hotspots. So to do this, there are two parts to it. One is to actually learn to predict the user's next location based on their current mobility trace. And this can be done in a federated manner, and my colleague Ming Zhao has done a lot of work in this area. So we're going to build on some of that work. The other thing that does need to be done here is to create a histogram, you need some kind of a central server. So once we've learned these federated learning models for predicting a user's trace, we're going to use that prediction and obliviously share it with the central server so we can do oblivious computation of histograms for mobility, based on mobility for hotspots. The key idea here is to use both infected hotspots as well as mobility-based hotspots to come up with a risk predictor that will in turn give the user a risk index. There's a lot of work to be done here. This is really just work that we've started doing. The last thing we want to do is to add another kind of risk which is based on sensing that you can do on the phone itself. So for example, one kind of sensing you can do on a device is to actually speak into a device and use that recording. In particular, my colleague Visar Beresha is an expert on using signal processing techniques for acoustic signals. And what we want to do here is to use phonation. Phonation is already known to be well correlated with respiratory diseases. So what we want to do is have a user phonate such as an ah into their mic for a certain period of time, learn the features from that phonation pattern, and then the key idea here is to train a model to predict a risk. And we could use existing data on these things, particularly age and gender-based norms, as well as risk models for COPD, chronic obstructive respiratory disorders, and so on that are correlated with speech, to have a proxy to estimate such a risk index for COVID-19 as well. The holy grail of this project is to put all three indices together and learn a cumulative risk score, and this again is also going to require federated learning because every user has only their data and one must figure out a model, a way to actually aggregate these models over all the users. What is really cool about this project is that we get to work with ASU's University Technology Operations Office and deploy this app, and actually even before we deploy it, we can test it in various stages. So the goal is as soon as we build this in an emulator environment in the lab using Android phones and iPhones, our next step is to use a small set of users where we can deploy this app via an API into ASU's mobile app, which is really widely used across campus, and then test various facets of our own development. And then hopefully in a year, we can actually deploy it across all users of the app. And that's where we're at on this project. There are several challenges, as I'm sure you've thought about during this talk itself. Certainly on the contact tracing side, GPS has a certain accuracy limitation, and that can limit proximity detection. In terms of trade-offs, you can give user a lot of privacy guarantees if you continually or more frequently change the Bluetooth key and the GPS Bluetooth key to actually encrypt the GPS. And that gives the user much better privacy guarantees, but there's a scalability problem there in terms of generating these codes. Finally, there's also the scalability problem in terms of aggregating for an arbitrary number of infected hotspots. Certainly, we're going to look at heavy hitters in that context, but these are generally real challenges in implementing this. On the device level, in terms of mobility, how do we combine infected hotspot histograms with a continually evolving hotspot histogram just based on mobility and to predict a risk is certainly not something I can claim we know how to do completely. And in terms of, we can always add to this problem by doing daily surveys, getting information on work location and so on, just putting more features in. And talking about features brings me to the model. At the outset, we're certainly going to start with a simple model, perhaps even a logistic model for aggregating these separate indices and combining them together to come up with one risk predictor. For the mobility, we're going to be using deep neural networks, including LSTMs, but there are multiple questions we can ask here, as in, should we predict separately and combine, or predict just one shot? There are many challenges in both cases, and these are the kinds of challenges we are addressing head-on right now in this project. And with this, I'll stop, and you can directly email me at this email address, and thank you very much.